Alright, so let's talk about differential equations. Now I'm going to start the same way that my professor started, was with this quote right here. So this is basically a Greek quote. I think it's attributed to Heraclitus, but like we don't know specifically who said it because like historical sources are kind of ambiguous, I suppose. But basically it translates to life is flux or everything is flux. And the idea with differential equations is that a lot of the times we don't know exactly how something's behaving, but we know how it's changing. Right, a lot of the times we can detect like a change in temperature or like how heat's transferring between objects or something. So it's really easy for us to be able to give a very concise description of how it's changing, and we want to be able to go from that description of change to a model of exactly what's happening. So basically when you're talking about like algebra or calculus, you're given some function, right, like some f of x, and then you're usually solving for the input. So right, like solve for x. So now we're going to be given the change, so some derivative, some like we'll just say nth derivative of f with respect to x, and then we want to go ahead and find the original function that generates this. And so at the beginning here, it's going to be a lot of basically like drinking from the fire hose. There's just so much like definitions and vocabulary and stuff that I like can't really write it all out. So basically what I'm going to do is I just like copied over the definitions from my notes right here. So basically we're just going to kind of run through these, and then we'll go through some examples, and then as we get further in, it'll be a lot more like here is one thing, and then going in depth with the beginning. There's a lot to cover in terms of just like how we talk about these things. So to start, this right here is the definition of a differential equation, and it's a lot of words, but basically what it means is that as long it's just an equation that has the derivative, at least like the first derivative, it could be a higher derivative of a function. It could be a function of one or multiple variables. It could also have that function. So basically, as long as our equation has some derivative in it, and maybe you could have f of x in it, it could have x in it, you could have anything. As long as it's an equation and it has a derivative in it, then essentially it's a differential equation. Now our notation from derivatives is kind of thinking back to calculus. We have the prime notation, and then we also have the Leibniz notation, which is like this d over dx, and then we also will see this dot notation. You'll probably see it in like physics classes if you come to take those. The over dot means a time derivative specifically. So like x double dot is the second derivative of x with respect to t, and if x is your position, this would be like acceleration or something. Now, when we talk about types of differential equations, usually we're going to be dealing with ODEs. Sometimes people just call this class ODEs. So an ODE is an ordinary differential equation, and that means it's a differential equation with a single independent variable. So basically the independent variable is what this is a function of, right? So if I have f of x, x is the input, that's the independent variable because f depends on x, but x does not depend on f. If you had multiple, then it'd be called a partial differential equation, and you'd have like partial derivatives. So if you think like if I have f of x comma y, then I would have like partial derivative of f with respect to x, and this is saying per unit change in the x direction, right? If I were to change the x by 1 unit but keep y constant, how is f going to change? And so we can have differential equations that take this form. We'll see that a little bit, but really we're primarily interested in ODEs. So if we call it a differential equation or just a DE, assume that we mean ODE because that's basically what we're going to be mostly looking at in this class. Now the order of a differential equation is the highest derivative that we see in here. So like for this differential equation right here, we have a third derivative here. We have, this is actually, be careful, this is a first derivative to the fourth power. So we say that this is third order. So now we can go ahead and look at some of these examples right here to kind of get started with classifying these. So right here, we can already see we have a first derivative right here, and then there's no derivatives anywhere else. So this would be first order. We'll just say like order 1, right? It is a ODE because we don't have any partial derivatives. The dependent variable would be x, and then the independent variable will be y because we have y as a function of x, right? We look at the derivative of y with respect to x, and because it's not a partial derivative, we know that x is the only independent variable. Or I actually have these flipped. X should be the independent and y should be the dependent. And looking over here, we can see that our order, that we have a second order because the highest derivative is the second derivative right here. It is an ODE once again because we don't have any partial derivatives. The independent variables are just x, and then the dependent variable would just be y. Now right here you can see that we just have Once again, we don't have any partial derivatives, so looking at ODE, the order is 1, and we have 2 dependent variables this time, so our dependent variables are x and y, and our independent variable is t. Looking at this one, we now actually have a PDE because we have one function with derivatives with respect to different independent variables. Another indicator is that instead of a d right here, we have the partial symbol right here. So the order is 2. Second order, our dependent variable is u, and our independent variables are x and y. 2 more real quick. The order here is 2. Second order, it is a PDE. The independent variables are t and x, and then the dependent variable is u. And then here again, we have another PDE where it's first order. The independent variables are x and y, and the dependent variables, it's not clear what they're a function of, right? This is one problem that you can actually have with PDEs. It's not clear if u is a function of x and y, or just a function of y, and it's not clear if v is just a function of x or not, but u and v, we can say at least, are our dependent variables. So going back up here, there are a few forms that you're going to see differential equations commonly written in when we give like theorems and things. So one right here is called differential form. So basically it takes the form that some function m of x and y dx plus some function n of x and y dy equals 0. We'll see other forms like the normal form here in just a second. So basically, if we want to put this right here into normal form, we can think of y prime as a dy dx, right? And so we can kind of informally multiply across the dx. It's not technically, like, that's not a rigorous way to do it, but it ends up working out. One way you can think about this is whenever we're multiplying across a dx and then integrating, we could do the same thing with the chain rule, right? So if I have dy dx is equal to like some function of x, right? Multiplying across the dx and then throwing an integral on both sides would be the same as if I did it quote-unquote properly, like I integrated with respect to x, so dy dx equals integral of f of x dx, and then because of the chain rule, these essentially cancel. So we could say that sine of xy dy minus 3y cosine x dx equals e to the x dx, and then if we subtract this across, we can put in normal form. We can say negative 3y cosine x minus e to the x dx plus sine of xy dy equals 0. And this right here would be our n, and this right here would be our m, and these are both functions of x and y. Another way you're going to see ODEs written is something called normal form. So basically what we do is we write the highest derivative, so the highest derivative as a function of all the other derivatives and x. So like if I have this function right here, my highest derivative is y triple prime, so I just solve this for y triple prime. I would get that y triple prime equals what? We're going to have to divide through x, so this is all going to be over x. We should have like y plus 3 plus sine x minus y double prime all over x, and this is a function of x, y, and y, technically y prime, even though there's no y prime in here, and y double prime. When we talk about defining the solution to a differential equation, basically we have to find some function, which we'll in our derivation call phi, but usually it'll be like f or something, all over some interval. So the key here is that not all of our solutions will be defined across the entire domain. We might have solutions that only work across a certain interval. We'll get a bit more into that later. And it needs at least n derivatives because we're going to substitute it into the ODE basically. So if I have like some differential equation right here, xy prime plus y equals 0, whatever I think my solution might be has to have a defined y prime in order to make sense, right? In order for me to plug it into the equation, right? So if I plug it into the equation and the equation holds, then we can say that it's a solution, right? So if I go ahead and I take a derivative of phi, and I have phi prime is negative 1 over x squared, and then if I plug that in right here, that would require that x times negative 1 over x squared plus 1 over x equals 0. This is going to be a negative 1 over x plus 1 over x. We get 0 equals 0. So this does check out. And the interval over which this is defined is basically going to be everywhere except 0, right? So we can say negative infinity to 0, union 0 to infinity. Now, a type of solution that you'll see besides just this particular solution is something called a general solution, which basically aims to give you a whole classification, like a whole family of functions that fit the differential equation, right? So instead of 1 over x, maybe our solution was like 1 over x, or like c. We'll just say c over x, where c is some constant. So this is basically defining some family of functions where we have a constant divided by x. And we call this a general solution because it's defining generally a whole classification of solutions. Now there's also the general solution, which is not just any general solution. It's the general solution that encapsulates every single possible solution to the ODE. So basically, the general solution encapsulates any particular solution that'll solve this differential equation. So one of the problems that you saw in calculus is that whenever you integrate something, like you go from the derivative to the original function, usually you get a constant out front, right? Because basically when you only have information about its changing, you can't recover all of the original function exactly, right? Like if I'm only looking at the speedometer, I can map out how my position of my car or whatever is changing across the entire trip. But if I don't know where it originally started, I can never say for certain where it is at any point in time. I just know how much it's moved, right? And so an IVP, or an initial value problem, is a differential equation together with a set of initial conditions that allow us to get a singular solution instead of like a family of solutions. Another thing to note, looking at like the more rigorous definition right here, is you can see that for an IVP, at least the ones that we're looking at and how we're defining it, all of our initial values are at the same x value. So you can see there's an x naught here, and x naught here, and all of them are also defined in terms of y, y prime, y double prime, and so on. So basically, the form of our initial values is we have some x value, and we're given that the evaluation of that value for several derivatives up to the order, right? So this is a second order, so we're given one at the, I guess you can call this the 0th and the first derivative. So up to n minus 1, which is why you see the n minus 1 right here, because we also have just the original function. That's one of our initial conditions, and that many n initial conditions is how many we need to fully describe this without giving a family of solutions. Because for each derivative, you can imagine that we're going to need to undo that sort of with an integral. We're not really going to integrate it several times over. We're going to see different methods for doing that. But you can imagine that for each integral we do, we're bringing out another constant, right? So if we have an nth order differential equation, then we're going to need n constants. We're going to have to solve for n constants, which means we're going to need n initial conditions or n other equations to define this function. Now, on top of quantitative analysis, sometimes we also want to do qualitative analysis of the ODEs, and so sometimes we want to be able to give like pictures or graphical representations of what's going on. And one kind of basic way you can do this is something called a direction field. So the idea is that if you have a differential equation right here, I can plot the slope at several values, right? So if I have a pretty simple one, y prime equals x plus y, then I can plot the slope across several x and y values to get an idea of what the original function might look like, right? So if we call this the x-axis and the y-axis, and we plug in a few values, so like if x equals 1 and y equals 1, then we have a slope of 1. Then we have a slope of 2, so we would go up like this, right? At 0, we have a slope of 0. This would be 1, and then the slope would kind of increase like this, right? Now here we'd have a slope of negative 1, negative 2, and so on. And if you kind of fill in the rest of this, of course I'm drawing it a little bit quickly here, but you could be a bit more careful. Maybe you could use like a plotting software, but you can kind of see that we're getting this idea of like where the flow of our function is going to be. Obviously this may not be exactly what's happening because I drew it kind of quickly. So with just the ODE, we get a general idea of where our function is, sort of the general behavior of our function. But now if we add in this initial condition, so in this case y0 equals 1, means that it would include the point 0, 1, so like right here. And then with that, I can extrapolate forwards So we can call this like in the positive x maybe. Then I could also extrapolate backwards. I don't know exactly what's going to happen. I think it's going to go up. But that's the basic idea, is now I can kind of see what this function looks like and what the general behavior of functions with different initial conditions look like. Now I am going to throw a little bit more at you. We're kind of at this like preliminary stage where there's just a lot of things that you need to know about, and there's not really a whole lot of like deriving or intuition or like big results that we get. It's just like throwing these terms at you pretty much. So a linear ODE is basically one that has this form right here. So you can see right here out front in each of these, out front in each of the terms, we have a function of x, right? So you can just think of this function of x, function of x, function of x. We're just labeling them an minus 1, all the way down to a1 and a0 equals a function of x. And then if you look at except for the function of x coefficients, we have a y, then a y prime, and then just increasing derivatives all the way up to the nth derivative. So basically some function of x times the nth derivative y plus some function of x times the n minus first derivative, adding all the way down until we get to some function of x times the first, some function of x times the just y, and then equals f of x. So this means that if you had a function of y, or y prime, or y double prime, or whatever, in here, then it would not be in linear form, right? If this was like y prime squared, then we wouldn't be looking at linear form. And specifically, we can say it's homogeneous if this f of x right out here happens to be 0. And because the word homogeneous shows up a lot in just a lot of places, engineering, math, whatever, and even sometimes it'll show up in different places in differential equations, it's specifically called Euler homogeneous because Euler. And then we call an ODE autonomous if it has the form y prime equals f of y. So this really only applies for first order. We're only going to see it a couple of times, I would say. It's not like one of the big things we'll look at, but it will come up later. So basically, y prime is a function of y. X does not show up in here at all, or maybe our independent variable is t. Who knows? And so yeah, that's it. A lot of kind of vocabulary-ish stuff, but it'll get more interesting the further in you get.